Hi, I'm Miguel Zumalacarregui, and today I'll be talking about attempts to solve the Hubble problem in theories beyond Einstein gravity. So, motivation for this work is that on one hand, we have a very successful description of the universe based on the LCDM model, which nonetheless requires two unknown components, dark matter and dark energy, that together constitute 95% of the energy density in the universe today. And while this model is very successful, there are several data sets that enter in tension when interpreted within this very simple framework, giving rise to discrepancies in the cosmological parameters. Perhaps the most serious of them is the difference in the Hubble constant, the expansion rate of the universe, as inferred by direct late universe methods and indirect early universe-based methods. Here I'm showing the results of these two probes as a function of time. And as the precision has increased, the values, this tension has become more and more apparent, and it's currently at the 4.4 sigma level. This could be due to systematics in either data sets, or it could be due to a true deviation in the standard paradigm. And future data sets, for example, gravitational wave observations, will allow us to address these with entirely different systematics and entirely different methods and verify whether this tension is real or not. So the first way to measure the Hubble rate is that I will call direct, consists in calibrating type 1a supernovae. And then once we know the luminosity, here L, intrinsic luminosity of the supernovae, we can relate it to the observed flux by this and infer the cosmological distances, which in turn give us the Hubble rate. This gives a value of 74, around 74 kilometers per megaparsec per second, which is higher than this other indirect method. Now, the indirect method relies on the cosmic microwave background, and in particular on the size of the acoustic scale. Here, this expression is for the angular projection of the acoustic scale, RS, which is itself given by an integral of the speed of sound in the baryon photon plasma divided by the Hubble rate all the way till recombination. So this angular acoustic scale we can observe on the CMB, and then we can observe on the distribution of galaxies through the baryon acoustic oscillation feature. And this can be done at different redshifts. So this method is shown by this other data points in this plot. The black line is the Planck values for predictions for the Hubble rate in LCDM, where all other parameters of the model are fixed. And these other points are different baryon acoustic oscillation measurements. Now, something that it's very important to keep in mind is that if we manage to change the acoustic scale, all these, the Planck line, and all these points can go up and down. This is very well summarized in this plot that I will be showing, and it's based on Lloyd Knox and Marius Milea's Hubble Hunter's Guide, where I'll be showing the Hubble rate and the acoustic scale for different models. Now, lambda, here the bands show model independent measurements. This is the horizontal bars are the supernova, calibrated supernova method. This slightly tilted band is the result of combining BAO and supernova without assuming any calibration, but just assuming that the cosmological distances inferred by both are compatible. So LCDM lies here. It has a low Hubble rate and a high value of the acoustic scale. But if we trust this model in the fairly model independent measurements, they point to the solution being a lower acoustic scale. And if we go back here, a lower acoustic scale means a faster expansion rate before recombination. This is something that has been very actively pursued in recent years. For example, in order to increase the Hubble rate, different groups have proposed an early dark energy model of the quintessence type, here shown by, characterized by a potential and a standard kinetic term, in which the energy density of the scalar field starts potential dominated, therefore behaves as a cosmological constant, and then around the redshift of equality, and this is important to fit all the data, the densities of matter radiation and the scalar field become comparable, and the scalar field begins evolving. And its evolution is so that it sort of defrosts at the equality era and then oscillates and decays away. But it injects enough energy to reduce the acoustic scale and increase the Hubble rate accordingly. So in the next few minutes, I will explore how different extended theories of gravity can help solve this problem in the late and the early universe. And in particular, I will present three general mechanisms. The first one is late universe phantom expansion that I'll call LUPE. The LUPE means magnifying glass in German. And this is at late times, having the universe expand faster. The second one I'll call imperfect dark energy at equality, or IDEE, also German for idea. And this is particular scaling of modified gravity energy density such that it always peaks at equality, which is what quintessence models seem to want to solve the Hubble problem. And finally, the third category of models that I'll describe is enhanced early gravity. This is just having the strength of gravity be stronger at early times, are therefore increasing the Hubble rate. Just to show you the final result, none of these models really works for one reason or the other, but they provide the first step towards finding this type of solutions. So let me present the framework. I will be working within Galileon gravity models, which can be thought, which emerge naturally as limits of other theories. For example, in extra-dimensional models like DEP, reduced to Galileon gravity, where a scalar field represents the embedding of the additional coordinates of our world in the extra dimensions. Importantly, Galileons recover GR to a good approximation on small scales, and the theory that I'll be considering is compatible with the speed of gravitational waves. So it's characterized by a coupling function and two free parameters, of which one can be rescaled by redefining the scalar field, which is completely arbitrary. And there are, of course, two initial conditions: the scalar field initial value and initial velocity. So for further progress, I will assume that the coupling function is an exponential, so which only depends on one parameter. This turns out to be a very convenient choice. And I will further rescale this Galileon coupling to -1 for full generality. Then there are two model parameters and two initial conditions that will determine the dynamics of this field, and will in and of itself give rise to these three different possibilities to solve the Hubble problem. So first of all is this coupling, the Galileon coupling here, C0, which most important property is the sign of it. So if this sign is negative, the sign of C2 is negative, then the energy density of the scalar field eventually starts rising. So it actually grows, and the field will take over the energy budget of the universe and can produce accelerated expansion. Now, if this sign is positive, as we might expect from, at least naively expect from stability, then this field always dilutes, and it dilutes very fast at late times, meaning that modified gravity in the absence of other terms like the coupling will become irrelevant. And among other things, we need a cosmological constant. So first, let's assume that the model is accelerating, it provides dark energy, and this gives rise to the first category of theories, the late universe phantom expansion. In this case, at least if there is no coupling, there's a very simple relation for the energy density of the scalar field today. It's just given entirely by C2. And if here I'm showing the Hubble rate and the equation of state for this model, keeping the physical parameters, the acoustic scale, projected acoustic scale, and the physical densities fixed. And you can see that because the expansion is phantom, the energy density of the field actually grows with time. It boosts the value of the Hubble rate considerably. And these lines are for different combinations between a cosmological constant and the scalar field making up the energy density. Now, long story short, there are a lot of interesting details to this model. I referred you to Rank 2017 for the details, but in a nutshell, this doesn't work for the models, Galilean models that are compatible with the gravitational wave speed. They predict an anti-correlation between the CMB and galaxies at low redshift. This is because the gravitational potentials grow with time instead of decreasing. And it's, so all the models I'm considering here are basically reduced to this orange dashed line, which is far away from the data. Well, if we could forget about that problem, this would otherwise be a nice solution to the Hubble rate, a late time solution. You can see in this diagram that it changes the Hubble rate without changing the acoustic scale, which would be here. But still, at least as far as the direct measurement is concerned, this seems to be an okay solution. Now, the second class of models that I'm interested in, I call imperfect dark energy at equality. And here I want to look at the, this is an early modified gravity model. So I want to look at the Friedmann equation, which in the theory can be decomposed in two pieces. So there is an overall rescaling of the strength of gravity that depends on the Planck mass, which is the coupling to the Ricci. This is easy to understand. If the this function is larger or smaller, this affects how matter will produce curvature. But there's also an additional contribution, rho phi, coming from the other terms. And in particular, this Galileon term, this nonlinear term, has the interesting property that the energy density, the kinetic energy, which is given by the initial derivative of the scalar field, always dilutes more slowly than radiation and faster than matter. So we can start with here the purple lines, situation where the scalar field is subdominant with respect to the total energy density, but it slowly takes over radiation, peaks around equality, and then dilutes faster than matter. This is best seen here, not in logarithmic scale. So the energy density of the scalar field is very small at high redshift. Then its relative abundance grows all the way until the equality era, and then is reduced. So in this other plot, I'm showing the posteriors for the Hubble rate compared to the initial energy density of the scalar field. The dashed line is what the relation that would follow from keeping the acoustic, projected acoustic scale fixed. And the purple contours is what Planck allows. And unfortunately, you can see that the model is restricted to the region where it basically does nothing to alleviate the Hubble tension. And the reasons behind this are interesting. This is a rich early modified gravity scenario, but basically it's because the modifications of gravity are proportional to the fraction of scalar field. And if you make it comparable at the order of a few percent, then these effects become significant. So this is sadly, well, and you can see here that these are the residuals on CMB fit. You can see that this is a very scale dependent effect that doesn't, cannot be easily absorbed by varying other cosmological parameters. So this unfortunately doesn't work when compared with the data. And the region it produces is very similar to the lambda CDM contour. Now, coming up to the third possibility to solve this problem, and my personal favorite is enhanced early gravity, which relies on the coupling between the curvature and the scalar field. And as mentioned before, this coupling affects the Friedmann equation. And affects the way that the Hubble rate responds not only to the scalar field energy density, but also to the standard matter density. So there are two parameters associated with this. One is the initial condition for the field, which basically sets the strength of gravity early on through this initial effective Planck mass. And then you can see here the evolution of the effective Planck mass for different models. The scalar field is frozen until a later time when the coupling becomes active, and then this constant beta tells us how much the field evolves, and then hence determines the final value of the effective Planck mass. So this is broadly the dynamics of the scalar field. And when we look at the energy density, it's very different from other models. So effectively, the energy density or the Hubble rate compared to lambda CDM is basically a constant throughout the early universe and well until after recombination. The fact that this is constant, it also softens a lot the modified gravity effects. And you can see here in this posterior that the initial value of the Planck mass determined by the initial value of the scalar field is very correlated with the Hubble rate. And while it doesn't go all the way to the direct measurements, it significantly enlarges the error bars and reduces the tension. There's a very interesting interplay between this initial Planck mass and other cosmological parameters, also involving Big Bang nucleosynthesis, which is affected by the expansion rate in the early universe. But when you put everything together, even if we only vary the initial Planck mass, as these solid lines for the residuals show, you get a modification that is much more, much milder than in other cases. And other early modification of gravity shown before. And in particular, once we account for other cosmological parameters to be varied, you can see in the dashed line, this is the best fit to CMB and BAO and direct Hubble measurement. You can see that it gives a much better fit to the data once the other cosmological parameters are included. Unfortunately, well, this model, its main drawback is that it goes against it is difficult for it, at least in its minimal version, to fit the late universe constraints and solar system tests of gravity. So looking at this Knox and Milea's Hubble Hunters plot, you can see that there's some improvement in the sense that this model goes towards the model independent preferred region, but it's not quite a solution. It's also possible to combine different solutions, in which case one gets this kind of things. But let me conclude briefly by saying that the Hubble problem is an interesting problem. I've shown different classes of solutions in a very simple modified gravity model that unfortunately only moderately solve the tension, and they're constrained by other methods. But testing gravity is easier now than ever, and this is only the beginning. So there's a lot to improve in terms of model building and etc. Thank you very much.